we'll just wait for a few more minutes to see if somebody else joins. Okay, let's start. Hello, everyone. This is Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So today we'll go over the questions of week 7 and then some questions that will help you solve the week 8 assignment. So let's start. Okay. Keeping all other parameters constant, if thrust is doubled, how many times will the takeoff distance, how much will the takeoff distance be? Okay, so in the previous week, we had seen that the takeoff distance, oops, the formula for takeoff distance, it was derived in the classes, and in the previous week, we had seen that, oops, why am I not able to? Okay, just give me a few seconds. Okay, so do you recall what the formula for takeoff distance was? Or what they're proportional or inversely proportional to? Takeoff distance, S takeoff was the formula we had derived. Just can you try and recall what all they were proportional to or inversely proportional to? All the terms that it depended on. So, okay. S takeoff, the formula that we had derived was 1.44 W by S rho G CL max inversely proportional to T. Yes, you're right. So here you have thrust loading. Okay. So in this question, they've asked about thrust. So as takeoff is inversely proportional to thrust. So if the thrust is doubled, as takeoff becomes 1 by 2 of as takeoff. Right? So it becomes halved. So it becomes half. Okay. Next, keeping all other parameters constant except the thrust, the ratio of takeoff distance in sea level and 5 kilometer will be. So here, what we need to see is the density. So usually I think the density would be given to you in the question. If in this case, you could have just Googled it, but in the exam, the density will be given to you, okay? So it's just the ratio of the densities. Again here, according to the formula, it's inversely proportional to the density. Okay, so you have as takeoff, let's say they've asked ratio between sea level and 5 kilometers. So sea level and S takeoff 5 kilometer would be density at 5 kilometer and density at sea level. Okay, I think in the solutions, this was given as the square of the densities, which is wrong. So I'll point it out to the TA who evaluates the questions, and that will be rectified. Okay, it's just the ratio of the densities at the two altitudes. So at 5 kilometer, density was given as 0.7, and at sea level, it's 1.225. So if you take the ratio, it comes to around 0.57, right? So that is the answer. Next, keeping all the other parameters constant, if the wing area is halved, how many times will the takeoff distance be? So again, takeoff distance, wing area, it's inversely proportional to the wing area, right? So S. It's inversely proportional to wing area. If wing area is half, so S becomes 1 by 2S. So S takeoff becomes twice of the old S takeoff. So it becomes twice. All right. Next question. Keeping all other parameters constant, if wing loading is half, how many times will the takeoff distance be? So it's directly proportional to wing loading, right? So if wing loading is half, the takeoff distance will be half. So it becomes as takeoff is half. Keeping all other parameters constant, if the wing airfoil is changed to produce twice the maximum lift coefficient as the first used, how many times will the takeoff distance change, right? Again, inversely proportional to CL max. So if CL max is airfoil is changed to produce CL max, then it's inversely proportional. So S takeoff will be 1 by 2. Okay, so these assignment was fairly simple. Let's look at the next questions. Okay, what type of airfoils are generally used in flying wing aircraft? I think we discussed these type of questions earlier on in the lectures. So what type of wing is generally used in flying wing aircraft? What would it be? Symmetrical, cambered, reflex? What will it be? Why cambered? If you think it's cambered, can you try to give a reasoning? If it's cambered or if it's symmetrical or whatever answer, can you try to justify the answer if it's cambered? Why did you say cambered? What was your reasoning? I think in week 2 or 3, when we were discussing airfoils and stability, we had looked into this. Okay, as in flying wing, no horizontal tail is provided. So if a horizontal tail was provided, what kind of airfoil would you use? Cambered. Why is this difference? What or like what is the difference between reflex and cambered? Why are we preferring a reflex? Reflex is the right answer, okay? So it is reflex. So why or how is the reflex airfoil different? You try telling me. What is the difference between reflex and camber that makes us want to use reflex for the flying wing aircraft? Just try referring to your notes, see the difference, different types of airfoils, or just Google it and tell me. Just try figuring it out. We had discussed, I think, the very same question. Yes. So one condition that we had seen, not condition, something that we required was CM not greater than 0. Why did we need this thing? So if this was your CM versus alpha graph, in this case, CM naught is positive. So if it was negative, this is CM versus alpha. This is case A, case B. So for case B, CM naught is negative, right? So this is your CM naught. And in the case of B airfoil, if you want to trim the aircraft, it will trim at a negative angle of attack, which is not desirable. But in the case of A, the airfoil A, you're trimming the aircraft at a positive angle of attack. So for this, what do we need? We require Cm not to be greater than 0. So for reflex airfoil, the Cm, that is pitching moment at AC, is greater than 0, is either equal to 0 or greater than 0. So if it's a cambered airfoil, positively cambered airfoil, your, and this is your AC, this is your CP. What was CP? What was CP? Center of pressure, right? So it's, yes. So it's where the forces are generated. But since the CP kept moving with angle of attack, we needed to come with a different term, a different point about which we can do our analysis. So that is your aerodynamic center. And this aerodynamic center is by definition the point which does not change with angle of attack. All right. So we consider our analysis at point AC, aerodynamic center. So what do? We have to transfer the aerodynamic forces and moments to the AC. So this lift and drag are transferred to the AC. So when you transfer the forces to another point, it also comes with a moment. And since this CP is behind AC for the case of a cambered airfoil, it comes with a pitch down moment. So in this case, Cm naught is less than 0. So that means you will have to trim your aircraft at negative angle of attack. So for the reflex airfoil, so you have something, there's an upward curvature towards the end, right? So it goes somewhere like this. What this does is it either makes the CP and AC the same point, or it moves CP slightly ahead of the AC. Okay, the upward curvature towards the tail ensures that the CP is slightly ahead of AC. What happens here is that now when the lift and drag are transferred to AC, it comes with a pitch up moment, which makes Cm naught greater than 0. All right, and then you can trim the aircraft at attack. Okay, yeah, so this was the slide that we'd seen in the first, second or third lectures. So the first, we had just gone over the different types of airfoils. Which one is reflexed here? So if this is 1, 2, 3, 4, 5, and 6, which is reflex airfoil? Fourth one, correct. Fourth one is the reflex airfoil. Yeah. So there's an upward curvature, slight upward curvature towards the trailing edge. I think somebody had defined this in one of the previous classes. It's an interesting definition where what they defined the reflex airfoil was where the camber line intersects the uh, mean chord line, right? I thought it was an interesting definition. Okay, so in this case, I think 1, 2, 3, and 5 airfoils. What is airfoil number 6? The 5 airfoil is symmetric airfoil, which we use for tail and the rudder, vertical tail, horizontal tail. All these cross sections are symmetric airfoils generally. Low camber, deep camber, we have seen all these types of airfoil. What is the airfoil number 6? What is airfoil number 6? We had discussed this also. It is thicker, but it had a name, right? So it had some attractive properties. Just try recalling. There's a particular type of airfoil. It is thicker, and hence it becomes lighter. We had discussed this, right? So the airfoil is thicker, and hence it is lighter because you need lesser structures to support it. So it is a lighter airfoil, lighter wing. So we had discussed these points. So if you observe the airfoil, it is flat on the upper surface, right? It's like a cambered airfoil, but it's slightly flattened above. And then the camber comes into play. So does that ring any bells? Do you remember hearing something like that? I think this slide we had looked into a couple of times in two different sessions, in fact. Supercritical airfoil, yes, perfect. So why do we need the supercritical airfoil? How does it help us? Delays drag. It delays the drag divergence Mach number, right? Yeah, so it increases the drag divergence Mach number. So what happens is this upper surface is flattened and the shock wave is also pushed aft. The formation of the shock wave is pushed aft. Flow separation happens later. So these were the properties. It delays the drag divergence Mach number, MDD. MDD is increased. Okay, right. Okay, let's look at the next question. At zero angle of attack, a lift coefficient of symmetric airfoil will be. Very simple question. Mm. 0. Yes, correct. So you have your uh, lift equation as CL naught, the CL alpha into alpha. In the case of symmetric airfoil, so this was your graph. CL versus alpha. This is symmetric. If it was cambered, it would be something like this. So for symmetric, you have CL naught is 0. And for cambered, you have CL naught is greater than 0. So in this case, for symmetric airfoil, it will be CL alpha into alpha. And if it is at 0-degree angle of attack, it will be 0. Okay. So 0. Yes, correct. For the given graph, the condition for CM versus alpha plot represented by the line A is. What is the right answer? C option. Yes, so dCm by d alpha is 0. What should the condition actually be? This is right, you're right about this. Option C, yeah. What should it actually be? For static stability, what should it be? What should it be for static stability, longitudinal static stability? Less than 0. Yes, so your CM alpha should be less than 0, right? For static stability, CM versus alpha, this should be the graph. Why should it be less than 0? Can you tell me physically why it should be less than 0? I think we'll deal with stability a little more in detail in the next week. I think week 9 lectures deal with stability, but this basics we had done earlier. So can you recall and tell me, physically, why should CM alpha be less than 0 for stability? Why should it be less than 0? Yes, maintain longitudinally stable, but physically, why? How does it make the aircraft longitudinally stable if CM alpha is less than 0? Can you try and explain it? So when I asked you which condition is for longitudinal stability, you said option B, correct. Can you physically justify that? How did we come up with it? For positive disturbance in angle of attack, negative CM is generated. Yes. So imagine your aircraft is flying and it's subject to a positive increase in angle of attack. To restore this disturbance, you need pitch down. You need CM, negative CM, right? So if your aircraft is inherently stable, it will produce a pitch down moment automatically. That's why you require CM alpha to be less than 0. That's perfect. Okay. Did the others understand what he has said? Okay. Let's move on. An aircraft with rectangular wing area 10 meter square and mean chord 1.02 meter. What is the aspect ratio? This again is fairly simple. You should be able to do it. Let's do it and tell me. One 1.61. What about the others? Tell me if his answer is right or if you're getting some other answer. Okay. Can you tell me how you got it? No, not Shreyash, but the other two. Can you try and tell me how? So what is the formula for aspect ratio? Oops. Yeah. So what is the formula for aspect ratio? B square by S. Okay. So what is B square here? Nine 9.81. How did you get? What is B? Correct. So yeah, you can get S is equal to B into C. From that, you can get your B. So your B is nothing but S by C. So S by C the whole square by S, right? So if you do this, you get S by C square, and that is 10 by, how much is C? 1.02 square. And so you get 9.61. Perfect. Both of you are right. Okay. Next question. A commercial airplane is landing with a touchdown velocity of 285 km per hour. The stall velocity during this maneuver will be. It's not really a maneuver during this mission, the touchdown. What will it be? So you have a direct relationship between the touchdown velocity and stall velocity, right? An empirical formula. Just use that and you'll be able to find out. There is an empirical relationship between V touchdown and Vs. Just try doing this, take a couple of minutes, look at the lectures, notes, and then you'll be able to do it. It's very simple. It's just this relation. So it's just V touchdown is 1.15 V stall, right? So V stall is nothing but V touchdown by 1.15, and that gives you 285 by 1.15. It's 247.8, but it's kilometer per hour. They've asked you in meter per second. So how do you convert it to meter per second? What is the answer? What is the answer in meter per second? It's 68.84 meters per second. Okay. Yeah, perfect. Okay. If the thrust to weight ratio of an aircraft is 0.05 and the aerodynamic efficiency is 10 and the turn radius during a pull-up maneuver is 500 meter, the flare distance of the aircraft will be. So flare distance is usually there. Where do you see it? In the, let me just see. So this is where we have encountered the flare distance, right? So flare is that curvature, right? So during a pull-up maneuver, you have a similar flare happening, right? So this is the flare uh, mission that's part of the touchdown region. So during pull-up, you will have a similar flare curve, right? So that's what they've asked you. So given this information, try to find out the flare distance. Try doing this. Okay. One clue here is that, so in this profile, the approach angle and the flare angle are the same. Okay, if you take the same, imagine this during a pull-up maneuver. Okay, try doing it now. That is the clue. The theta approach and theta flare are same. You do it now. Finding the approach angle we had seen in the last week. I think it was part of your assignment, right? You try doing it now. What was the approach angle formula? We'd done this in the last, I think it's part of your assignment. What is the approach angle formula? Uh, Sine theta A. What was the formula? Please go back and look at the questions of the previous assignment, and then you might be able to do this, or the previous notes of the previous session. Approach angle formula, what was it? It was the negation of this. This was the climb angle formula, right? So climb angle sine gamma was T by W minus CD, or D by W, and then it became T by W minus 1 by L by D, right? So sine theta A was the negation of it. It was 1 by L by D minus T by W, correct? So let's try doing this. 1 by L by D is 1 by 10. Aerodynamic efficiency is L by D. Minus T by W is 0.05. So this comes to 0.05. Now, so they've asked you the flare distance. They've asked you this arc length. What is it? So if I say SF as the flare distance, it will be just R sine theta F. And R is given to you as 500 meters. So 500 into 0.05, which is 25 meters. Yes? Is this, were you able to understand this? It's clear? Right. Next question. To execute the takeoff maneuver, which are the control commands that are required? Is it only elevator rudder, elevator aileron only, elevator rudder throttle? Which would it be? Which one would it be? You know you require the throttle, right? So it has to be the last option, but can you justify it? Why do we need elevator? Throttle you need. Yes, it's pretty obvious. What about elevator? Why do we need elevator? It has to take off. You need to pitch up, right? That's also obvious. What about rudder? Why do we need rudder? So throttle and elevator we understood. Correct? Why do we need rudder? There are a few reasons. Can you try telling me some of them? For maintaining direction. Okay. So if I don't deflect the rudder and I am taking off straight, so why would I have to deflect the rudder? If I just keep the rudder as it is, no deflection, and I'm taking off straight, why would I have to, I will maintain direction, right? Why? During takeoff. So why would I have to deflect the rudder? You are right, that's one of the reasons, but tell me, explain a little more. In case of crosswinds, yeah, so gusts or crosswinds, yes, that's one reason. So reason one is crosswinds. Okay, now let's say in the absence of gusts or crosswinds, even then the rudder is deflected. Why? Think about it. If there are no crosswinds, even then the rudder is deflected. Why? It's something to do with the propulsion system. Think about it then, if that is a clue. Single engine failure. Okay, that is one of the reasons. Fine. Okay. Anything else with the propulsion system in this engine terms only? So there are rotating parts in the engine, right? So in case of any type of engine, so can you think about along those lines? So if all the engines or if there is just one propeller in the at the nose or pusher or puller type, if it's rotating in one direction, there will be a net torque, right? So to negate the net torque, you deflect the rudder. Another reason is something known as a spiraling slipstream. Okay, so let's look at that. It's called spiraling slipstream. What this is see, if there is a propeller in the front, in the nose of the aircraft, it's pushing the wind, right? It's pushing the oncoming air. And this oncoming air is thrown into a spiral around the body of the aircraft, around the fuselage, and such that it travels downward and impinges on the tail at a particular angle. In this case, it's impinging like this, right? So then the rudder would have to be deflected to maintain the direction. So maintain direction is the right answer, but what are the reasons why the direction would not be maintained? So this is the spiraling slipstream. So these are some of the reasons why the rudder is deflected. So you need to have the elevator, rudder, and throttle during takeoff. All right. Okay. Now just have a look at this airfoil cross section. Okay. So just observe it carefully, and then we'll look at some questions regarding this. Just observe it for a while. So what kind of airfoil is this? Symmetric, cambered, reflex, what is it? Or supercritical, what do you see? It's a simple cambered airfoil, right? Simple positively cambered airfoil. Alright? So now look at these graphs and we need to try to identify what each graph is. I think I'm missing one axis here. So that is the zero, that's the y-axis, alright? I missed that. Try identifying each of these graphs. Let's label each of them. So this is 1, 2, 3, and this is 4. Take some time, figure it out, and tell me which one each graph is. Okay, so Shreyash says first is CL versus, let me just write that down. This is CL versus alpha. Second is CL versus CD. CD, okay. CL versus CD, okay. Third is CD versus angle of attack. CD versus angle of attack. And the last is CM versus alpha. Okay. Let me look at it. So CL versus alpha, I think it's fairly simple, right? So cambered airfoil, you have CL naught is greater than 0, which is what is here, and then you have somewhat linear profile, and then it proceeds to stall. Correct? This is what we've seen for a cambered airfoil, which is very evident here. Okay. Then second one, it is CL versus CD or CD versus CL. So what's on the x-axis? Okay, yeah, you're right. Yeah, CL versus CD, the drag polar, right? So this is the drag polar, correct? Oops. So this is the net. Just a minute. I think there's some noise coming. Just give me a minute. Sorry about that. Let me just get back to this. Yeah, okay. So this is your drag polar. You're right. Okay, CD versus alpha. Again, you can see the bucket, the drag bucket, right? So that is what tells you that it is CD versus alpha. CM versus alpha, you have what is characteristic of cambered airfoil during for CM versus alpha. Your CM naught is less than 0. Sorry, is less than 0. Correct. So here you can see that the CM naught is here. It's less than 0. Okay, and then it is not stable or unstable. It depends upon the characteristics of CG and aerodynamic center. All right. So here in this case, it's a positive slope, so it is unstable. But your CM naught is less than 0. That is what is characteristic of a cambered airfoil. Okay. Now, yeah. So now let's just look at this airfoil. This is symmetric airfoil. Since you did the cambered airfoil, you should be able to do the this one very simple. Right? Symmetric airfoil. Most of your graphs, in fact, all of your graphs will be symmetric about some axis. You should be able to do this easily. Okay, just look at these graphs. Okay, let me number them. This is 1, this is 2, this is 3, and this is 4. Try doing this. This time it would be nice if somebody else answers because he has already answered the cambered airfoil, so it will be easier for this one, right? It follows the similar pattern, but it will be much clearer in the case of a symmetric airfoil. Okay, let's move on with this. The first one is CL versus CD, right? So it is very similar to the previous one. Let's just look at it. Oops. Yeah. So it has a similar bucket. So CL versus CD, right? So this is up with this. Yeah. So CL versus CD. Second one, again, it has a drag bucket, which is very evidently seen here. So it is CD versus angle of attack. Third one is the symmetric airfoil. So fourth one is CL versus alpha. It's very simple, right? CL versus alpha. It has 0 CL naught and it has a fairly linear curve after that till the stall. Correct. So this is CM versus alpha, right? So it has 0 CM naught, which is typical of a symmetric airfoil. And then in this case, it is similar. It has a negative slope, correct? It has a negative slope, so it is stable. Can you try and tell me what these points are? There's a this sharp change in the slope in the pitching moment, right? In CM, change in the slope of the CM versus alpha curve. Can you try tell me why this change is happening? Why is the sharp change? Very pronounced sharp change in the slope. It's the negative slope till then, and then it's a positive slope. And on the both right and left, right? Symmetric, almost symmetric. Can you try telling me why? A sharp change in slope. What could the possible reason be? Also there in the case of the cambered airfoil, if you notice, so it's not symmetric. It doesn't happen across the zero line, the x-axis, the y-axis, but those sharp changes in the slope is visible even in the uh, cambered airfoil case. What are they? What could the possible reason be? Can you try and tell me? So it's because of the flow separation, right? Boundary layer separation happening sharply at those points. So that is kind of where the stall happens. This graph is not to scale, but so it's where the flow separation happens. The boundary layer is separated, and at that point, there's a sharp change in the pitching moment that is observed on the airfoil. It's not symmetric in the case of the cambered airfoil, but it's very evident even there. All right. Okay. So now let's yes. So this was the question that we had done almost we completed it almost completely. We just had the wing area and the wing chord and the wing aspect ratio left, right? So everything else was done. Let's just briefly go over this. I think somebody had pointed out in the questions that in the forum that there are some topics that are being dealt with in the sessions that are not taught by Sir, right? So I think while we began this aerodynamic center neutral point calculation, I had mentioned that it's just to revise the concepts that you had studied in the prerequisite courses, that's stability control and airplane performance. So we have studied some concepts there. This will help you to see with the numerical values that it help you get a feel, right? The aerodynamic center and the neutral point calculation. So it will not necessarily come in your exam. It will not obviously come, this long calculations will not come in your exam. But I believe it makes this course a little more fun and more practical, right? So it's not possible for sir to do all of these questions in the class. So I thought we could try doing it here. It's not for the exams, but it's just to fortify your concepts. Okay. So we'll just go over this. I'll just go over briefly how we did the questions, how we solved the neutral point, the formulae. Okay, and then we'll complete this question. We've been at it for quite a while now. Okay, so here there are 4 aerodynamic structures. One is the canard, 2 wings, and a tail. Okay, so we began with finding the formula for x bar and xnp. Okay, we find the formula for xnp and then we put in numerical values to get the exact value. So for that, we started with the aerodynamic forces and moments. So we first wrote the moment experienced at the CG. We wrote the formula for that. So what all contribute towards that? Lift on wing 1, drag on wing 1, lift on wing 2, drag on wing 2. I think I should use a different color. Just erase this first. Okay. So yeah, lift, drag on wing 1 and wing 2. And then you have moments on both the wings. These are also seen at the CG. Then you have lift on the canard, lift on the tail. There are no moments on the lift and the tail because both are symmetric airfoils. Similarly, the drag effects are not taken here because the drag is acting along the, you assume it to be acting along the CG line. Okay. Okay. So, and then we wrote down the moment experience at the CG. Then we wrote the non-dimensional parameters. So for that, we divided throughout by this half rho v square SC bar. And we finally got the CM-CG equation. Now that was split into CM naught and CM alpha. CM naught are the terms that are independent of angle of attack of the wing. And CM alpha are the terms that depend on the angle of attack of the wing. Okay. Okay. So this is your CM alpha equation, which at neutral point would be 0. So at CG equal to neutral point, CM alpha is 0. So you substitute these values into your CM alpha equation and you get a term for XNP, correct? You get an equation for XNP. Now, in this equation, what are the unknown terms? What do we have to find out? You need to find out CL alpha of the wing tail canard, X bar, the location of AC, not X bar, XAC, location of aerodynamic center of the wing, tail and canard, area of the wing, tail and canard, and mean aerodynamic chord of the wing. Mean aerodynamic chord, correct? Okay, mean aerodynamic chord of the wing. So first we started with the canard. Now in the question, there was a table given that gives you the shape of the wing, the geometric dimensions of the wing, tail and canard. Okay, using that, we found out the area of the canard, CL alpha. So all of the CL alphas given to you in the question were of the airfoil cross section. Okay, so we need to find out the 3D, the CL alpha of the wings. So we did that. Then we used, we found out the aspect ratio, and using which we got the mean aerodynamic chord of the canard, then location of the mean aerodynamic chord. Similarly, we did it for the tail. Now doing for the wing was left, right? Let's just do it for the wing. So what all did we have to find out? S wing. What is the area of the wing? How do you find out this? So let's just draw the wing first. Okay, so in the question, a taper axis was mid chord. Okay, taper axis was mid chord, root chord was 1, and the taper ratio was 0.5. So if it's tapering along the mid chord, it would be something like this. Right? It would be something like this. It's tapering along the mid chord. Fine. So your root chord is 1 meter. Taper ratio is 0.5. So taper ratio, what was the formula? What is the formula for taper ratio? Lambda equal to What is lambda equal to? CT by CR, correct. So you have CT divided by CR equals to 0.5. So your CT is, it's just 0.5, right? So this small distance is 0.5 meters. All right. So now let's find out the area of the wing. Let me just erase these extra parts. And let's split it into two shapes. So it makes it easy for the area calculation. Okay. Okay. Now S wing. How do you find out this? Area of the wing is? The span of the wing was also given to you, correct? So span is 4. So let's take area of the rectangle first, the blue rectangle. It's just 4 into 0.5. Then what about the triangular areas, two triangular areas? Plus. So area of this triangle, let's find out that. That one. So it's just half, base is again 4, altitude is 1 minus 0.5. Correct? Is it correct? It will be 1 minus 0.5 by 2. And since there are two triangles, it will be into 2. Is this correct? Please to correct me if I'm going wrong. Is this correct? Does it logically make sense? Is it correct? Yes. Okay. So can you tell me this value? Let me try calculating it. Meanwhile, you also tell me if I'm right. I've got 3. Is it right? 3. Okay. Now aspect ratio. Aspect ratio of the wing was what? B square by S. The span is 4. 4 squared by 3. What is the value? 16. 5.33. Okay. What did we have to find? What was next? Yes, CL alpha 3D is CL alpha 2D by 1 plus CL alpha 2D by pi E AR. Now what is CL alpha 2D? Oh, 6. So 6 by 1 plus 6 by pi E was 0.9. Aspect ratio is 5.33. Oops. Can you calculate this value? Let me just get the charger. Just calculate this value and let me know. Okay, what was this value? Where were we? Yeah. So what was this value? 4.29. Okay. Okay, next, what do we have to find out? What is the next step? We need to find out C bar, right? C bar. What is C bar? What was the formula? It was 2 by 3 CR 1 plus lambda plus 1 lambda square 1 plus lambda, correct? Can you substitute the values and tell me what the answer is? What is the value? C bar. So this is another term that we need to find out, right? For all of your terms, it's all divided by C bar. So C bar is very important here. What is the value? So it's 0.778. Okay, let me just mark that we have found that. Yes. Cl alpha we've done. S we have done. We need XAC wing. Okay. Let me remove some terms from here. Okay, let me remove the lambda. I hope you'll remember that. And let me remove the shading because we'll have to draw. We'll just draw that again. Okay, something like this. All right. So now we found out C bar, we need to find out XAC. So XAC wing, what would it be? So if this is your C bar, this is your C bar, your aerodynamic center is at the quarter chord point, right? So what is the distance from the leading edge? We need this. Okay, again, let me use another color. We need this distance. That is your XAC wing. XAC wing. So that is nothing but this distance in orange plus distance in green, correct? Distance in green is nothing but C bar by 4, correct? C bar by 4. What is the distance in orange? What is that small orange distance? It is CR by 2 minus C bar by 2. Is that correct? Just look at it. So taper axis is mid-chord. Remember that. So this is CR by 2, correct? And this is C bar by 2. Now does it make sense? Is my XAC wing formula correct? XAC wing. Yes? Okay, now can you tell me this value? What is this value? C bar by 4. What is the value? Can you tell me what the value is? This C bar by 4. C bar. Point 0.306. Okay, let me just circle the values that we want. And CL alpha and C bar and S. All right. Okay, so we have found all the terms. Now let's substitute it in the equation and see if we get the X and P. All right. So let's try doing that. Now, where was our form? This is going to be a little difficult. Okay, so 0 is 2CL alpha wing. 2CL alpha wing. I'll try to do it quickly. X NP minus XAC wing by C bar. X NP minus XAC wing by C bar. Minus CL alpha tail XAC tail. CL alpha tail XAC tail minus X NP by C bar plus CLAC. CL alpha tail. What was inside it? Okay, XACC plus X NP by C bar SC by S. Now let's substitute the terms. 0 equals 2 CL alpha wing is 4.29. NP minus XAC wing is 0.306 by C bar was 0.778 minus CL alpha of the tail was 2.9. XAC tail 4.575. XNP by C bar is, okay, C bar is the same as tail 0.45 by 3. Canard 3.34. Canard is 0.25. Okay, so the only unknown in this is XNP. You should be able to find this out, right? It's fairly simple now. Okay, so you'll be able to solve this, and this is how you find out the XNP. This is how the actual calculation is done. So this will not come up for your exam, so please don't get worried about that. But this is just for you to get a feel of the numbers and how the calculations are actually done. You can see here how smaller the tail and the canard are compared to the wing, right? See the area. Area of the tail is 0.45 and area of the wing is 3. Similarly, for the canard, it's 0.25 and area of the wing is 3. See the ratios, how much the wing is bigger, right? So this is just for you to get a feel of the numbers. Now, since we have some more time, we'll just do another aerodynamic center calculation. Before that, we'll just recall the terms here. So this is how we did the aerodynamic center calculation, which is, since we have done this so many times now, it should be very familiar. So you have an empirical formula for C bar. You have empirical formula for, it was another term, right? Okay, we're not using that YMAC. We are only using XMAC in the calculations. Okay, so now let's try doing this. I'll just draw one figure. It should be symmetric. Just spare my poor drawing. All right. So imagine you have this structure and you have this is 675. This is also 675. And you have 110. You have the entire CR to be 800. And what else would we require? Yes, so this would be 37 degrees. And they've asked you to find out C bar XAC. How will we proceed with this? Okay, so let's divide the section into two separate areas so it makes it easier. So this is 1, this is 2. Okay, let's try doing it for section number 1. Area of the first section. How do you find area for trapezoid? What is the formula? So it's half into sum of the parallel sides, right? So in the first case, let's take this quantity to be x. How do you find out x? So let me just write the formula and then we'll move on. Into 675, correct? Is this correct? So half into sum of the parallel sides into the altitude, correct? The perpendicular. Okay, how do you find out x? Just take a couple of minutes and tell me how to find out x. Have you been able to find out how to find that x distance? Okay, look at the angle that is given to you, and how about this distance y? Can you find out that y? So y is nothing but tan 37 into 675. Correct? So that comes to around 508.65. So now what is x? It's just 800 minus y, right? So it's 800 minus y, and that comes to around 291.3. Correct? Okay, so now just substitute the value here. What is the area that you get? You get a fairly big term. Okay, just calculate that and keep it. Next step is finding aspect ratio. That is B1 square by S1. And here B1 is 675, right? 675 square by S1 you would just have calculated. Next step would be finding out lambda 1. That is CT1 by CR1, and that is CT tip is the x distance, 291.3, CR is 800, and that is 0.36. Correct? Now let's find out C bar. C bar, what is the formula? Empirical relationship, 2 by 3, CR1, 1 plus lambda 1 plus lambda 1 square, 1 plus lambda 1, 2 by 3. I'm sorry about that. Okay. This is C bar for 1, section 1. So it's 2 by 3. CR1 is 800. Lambda 1 is, so it's basically 1.36 plus 0.36 squared by 1.36. This comes to. Similarly, we need to do it for the second section. Okay, so S2, again it's a trapezoid, so it's half sum of the parallel sides, that is 291.3 plus 110 into 675. So you get some term here. Then next step is aspect ratio. AR2 is B2 square by S2. You get some quantity there. Next is lambda 2, CT2 by CR2. CT2 is 110. CR2 is 291.3. How much is this? Get 0.37. Then mean aerodynamic chord of the second. Again, the same formula. So you get 2 by 3 into not 800. CR2 is 291.3. In brackets, you get 1.37. Let me just write it below. 2 by 3 into 291.3. 1.37 plus 0.37 squared by 1.37. You get some quantity. And then you need to find out mean aerodynamic chord of both the sections. How do you find out this? I had told in the last, I think, couple of weeks ago that it's a weighted average, right? It's a weighted average. Correct? How would you do this? So it will be S1 C1 bar plus S2 C2 bar by S1 plus S2. So what is this value? So now that you have all the formulae, try solving it and we'll complete these numerical values in the next session, okay? You have all the formula given to you here. Just calculate it. They'll come out to be big terms. At least the areas will be large values. But the C bar would be a small term. And then find out X bar, XAC also. They've asked you to find two things, right? XAC. How will you do that? So XAC, let me take another color. So XAC, let's just say, okay, let me, is this, so section 1. So this is your C bar, okay? And this is your aerodynamic center. And now you need the quantity from leading edge. You need this line in green. That is your XAC. So let me erase this. Your XAC is the line in green. XAC equals, so this small orange line plus this distance. So what is the distance in black? It is just 800 minus C bar. And distance in orange is C bar by 4. Correct? So now you have all the formulae, just plug in the numerical values and come to the next session, and then we'll be able to solve it. All the formulae are written here. Is XAC clear? Yes, okay. So if there are no doubts, do you have any doubts from this session? Okay, so if there are no doubts, we'll end the session here. We'll just verify the numerical values of this question in the next session, and we'll move on, okay? So if there are no doubts, we'll end the session here. Thank you very much. And all the best for your assignment.